So in this video, we're going to do a cool application to physics, which is called Fermat's principle of least time and also Snell's law of refraction. Now, what is refraction? So let me give you a simple example. I have here a glass of water and I have my finger. Now watch as I move my finger behind the glass of water. My finger disappears. As I continue moving it, actually it gets like a reverse image. But you know how when you have something in water, I don't really have a stick. You know how if somebody's standing in a swimming pool, their lower body looks shifted a little bit. So things look funny when you look at them through water. So this is due to refraction of light. So light travels in a straight path to the water-air interface, and then it travels in a different straight path below the water. So let me draw a diagram of this to show you what exactly is going on. Okay, so we have something like this, and then we have halfway through a medium interface. So the top part we have, we'll call this medium 1. And then below the line we have medium 2. Medium meaning air, water, syrup, Tabasco sauce, whatever medium the light's traveling through. Is it traveling through a vacuum? Is it traveling through air? Is it traveling through nitrogen gas? Is it traveling through liquid water, salt water, something like this? So we have two different mediums through which the light ray will travel. And the light ray travels from P1 to P2. So we have maybe something down here that you're looking at, and you're going to see with your eye up here in P1. So maybe medium 1 is air and medium 2 is water. So what's happening, and we'll also arrange this so that this distance we'll call A, and then this distance we'll call A. So we'll say that the medium interface, so the interface between the two mediums, is halfway between this vertical distance from P1 to P2 like that. And we'll normalize this so that this length is 1. So instead of having a second parameter, we'll scale length so that we define one unit of length to be this horizontal distance between the 2 points. And then we'll define the vertical distance as 2a in whatever units that is. So what happens is something funny happens. Light travels like that, and then it travels like this. So you notice that light's not traveling in a straight line from medium 1 to medium 2. It's traveling like that, and then it goes like this. And we'll call our variable x will be the distance at which the light ray passes through the interface. So this is x right there. And then let's also draw vertical, kind of just to get our bearing. Okay, so this angle right here we'll call theta 1, and this angle down there is theta 2. Now this phenomenon occurs because light travels at different speeds through different mediums. So the speed of light, 299,792,458 meters per second, is just the speed of light in a vacuum. So when photons are traveling through air, they're traveling at a slower speed. When they're traveling through water, they're traveling at a slower speed. In fact, when I was an undergraduate, I did a project where we worked in the nuclear reactor lab at Michigan. And so they had a nuclear reactor, and it was under like 20 feet of water. So you could actually look directly at the reactor. And the shielding was not done by lead, it was done by water. And it had this blue glow to it. And the explanation for the blue glow was that the nuclear reactor was generating photons that were moving faster than the normal speed of light in water. So they weren't moving faster than the absolute speed of light, but light travels slower in water, and this reactor is producing enough energy that the photons were traveling faster than how fast light normally travels in water. And so that blue light was almost like a sonic boom you would hear when an aircraft travels faster than the speed of sound. So it was kind of a similar phenomenon where you got this blue light. So just a little side story. So anyway, as I was saying, what causes this is that light travels with different speed through different mediums, speed V1 and V2. So let's say through this first medium, which in your mind you can just think of air, light travels with speed V1. And then the second medium, light travels with speed V2. Now, this plays into Fermat's principle of least time, so which basically says the path that a photon actually chooses is going to be the path that minimizes its time. So light travels along the path that minimizes its time. So you can think of this like if you're on a road trip and you have your GPS. You can set the GPS to have minimum distance. Just get me to my destination in the shortest physical distance. But maybe that might take longer than another path. So the shortest physical distance would be just a straight line connecting P1 to P2. But if there's traffic along that path, there might be in terms of distance, a longer path that takes shorter time. So this is the longer path that takes shorter time. So of all possible paths that this photon could have taken between P1 and P2, this path here is the path that minimizes the amount of time it takes to get from P1 to P2. Pretty incredible. That's how somehow nature knows to work that way. Okay, so this is also related to something called Snell's law of refraction. So Snell's law states that the ratio V1 over V2 is equal to the ratio sine of the angle theta 1 divided by sine of the angle theta 2. So basically, the angles theta 1 and theta 2 are situated so that the sine of this angle divided by the sine of that angle is equal to speed 1 divided by speed 2. So that's Snell's law of refraction, which can then be used to deduce the angles. So this is what we're going to try to prove in this video. And Snell's law follows from Fermat's principle that this point where the light photon hits the interface occurs at the single point that will minimize the total time required to get from P1 to P2. Another application or another story for the same problem is, suppose you're in a boat and you're out here at sea and you're in a contest to get to P2. Or, maybe there's some treasure here, or you're on a game show or something and it's the first person to get there. And you can travel so fast, you're in a little boat, and you can travel at a certain speed through the water, and then once you get to the shoreline, you can run a different speed on the land. So most people would probably just aim straight at that point and go this way. It's actually faster if you aim, there or maybe here, depending on, the ratios of V1 and V2. So the same sort of thing. Light somehow seems to do this automatically. Okay, so let's clear some space now that we kind of have our bearings. And first we have to formulate time. We have to figure out, well, how long does it take to travel from P1 to P2, assuming that we have a value of x. Okay, so first of all, we need this distance. Well, this distance right here is going to be the square root of a squared plus x squared, right? Because we have a right triangle, we have a here, x there. And this distance is the square root of a squared plus 1 minus x squared, right? Because if this length is x, then the other length is 1 minus x. Okay, so now we can figure out the total time. Because time, we know that distance is equal to rate times time. So the distance is your rate times your time. So the time that it takes to travel is going to be the distance divided by your velocity. So the total time as a function of x is going to be the distance, this distance, which is square root of a squared plus x squared, divided by the speed v1 that you're moving through this top part, and then plus this distance, square root of a squared plus 1 minus x squared, divided by your second speed v2. So this function tells us exactly how long it takes to get from p1 to p2, depending on where your point x is at which you pass through that interface. Okay, so next we need to take the derivative of this and set it equal to 0. Obviously our boundary is 0 and 1, so we're looking for critical points between 0 and 1. Okay, so we're going to need to use the chain rule. Let me clear all of this away. All right, so in fact, let me move this up here. All the way up top. And let's get rid of this stuff down here. Okay, so that's under the square root. Okay, so t prime of x. Okay, we have the square root of something. So remember the derivative of the square root of x is 1 over 2 root x. So this is going to be 1 over 2 square root of this stuff times the derivative of the inside. Now the derivative of the inside is going to be 2x. So that 2x will cancel with the 2 in the denominator like that. Then we get cancellation here and here. And then the similar thing goes for the second term. We get plus square root of something, so that's 1 over 2, the v2 stays along, square root of a squared plus 1 minus x squared, then times, only you might have been confused, it's 1 minus x quantity squared. Because remember that represents this length, and this distance was 1 minus x. That's 1 minus x. So you get 1 minus x squared plus a squared square root. And so then times the derivative of the inside. Now the derivative of the inside here is 2 times 1 minus x to the 1 times the derivative of 1 minus x. So that's negative 2 times 1 minus x. Because just taking the derivative of 1 minus x squared itself requires the chain rule, so it's 2, 1 minus x times the derivative of the inside, which is negative 1. So again, the 2's cancel, and so we get x over v1 square root of a squared plus x squared minus 1 minus x over v2 square root of a squared plus 1 minus x squared is equal to 0. So we set that equal to 0. So therefore this must, since it's this minus this stuff, this must equal this. So we get x over v1 square root of a squared plus x squared has to equal 1 minus x over v2 square root of a squared plus 1 minus x squared, like that. So this is the condition that we have to have in order for you to have a critical point in the total time it takes. So what can we do with this? Well, motivated by Snell's law, let's try to form the ratio of v1 over v2. So v1 over v2, move the v1 up here, the 1 minus x has to come down, so it's going to equal x over 1 minus x. That's going to equal square root of a squared plus 1 minus x squared over square root of a squared plus x squared. So now let's try to relate all this back to theta. So we have these right triangles in here. So what can we do with them? So we know this length, which was square root. So this one was the square root of a squared plus x squared. And then this length here was the other one, square root of a squared plus 1 minus x squared, like that. That was this one right here. Okay, so theta 1, what is the sine of theta 1? Sine is opposite over hypotenuse. This length is x. So sine of theta 1 is going to be, sine of theta 1 is just x over square root of a squared plus x squared. Now note that we have x over square root of a squared plus x squared right there. So that ratio is going to equal sine of theta 1. Similarly, sine of theta 2, well, here's theta 2, opposite is 1 minus x, and then the hypotenuse is this. So sine of theta 2 is 1 minus x over the square root of a squared plus 1 minus x quantity squared. And notice that we have that ratio in the denominator right there, this over that. So using this observation, we see that v1 over v2 has to equal sine of theta 1 over sine of theta 2. And that recovers Snell's law. Now I'm pretty sure that Snell came up with this relationship much before, in advance of the development of calculus. So it's pretty incredible that he came up with this, where really the simple way to see why it's true is with calculus. So we took the derivative, set it equal to 0, and we recovered this famous result in optics.